Hello students, this is Professor Chalai, and in this video we're going to look at atomic mass. In our previous video, we stated that pretty much all of the mass of an atom are located in the protons and in the neutrons. In fact, the mass of a proton is about 1.67 by 10 to the minus 27 kilograms. And this is actually true for the neutrons as well. They start to vary in a fourth significant figure, but to three significant figures, the protons and neutrons have about the same mass. Now, these are very, very tiny masses, and they're hard to keep track of and to add them up whenever we're thinking of the the masses of atoms. So really, to simplify them, because they both have about the same mass, we're gonna call instead of stating the mass in kilograms, we're gonna change the units to atomic mass units, or AMU. So they're both roughly equal to about 1 AMU. AMU just stands for an atomic mass unit. So the protons and the neutrons have about a mass of about 1 AMU. Just for reference, the electron is roughly 2,000 times lighter or less massive than a proton or a neutron. So let's look at the atomic mass then. Earlier we looked at how the mass number is the number of protons plus the number of neutrons. Well, really the atomic mass is just the mass of an atom, protons plus neutrons plus electrons, expressed in atomic mass units. So it's the mass of an atom, mostly just protons plus neutrons, in atomic mass units. Right? Because the electrons are so light, you need a lot of electrons to even change the atomic mass. But it's roughly the number of protons plus the number of neutrons. Since they're not exactly one, but very close to one, you get almost whole numbers. However, we talked about isotopes, and an element would have the same number of protons, but they would have different number of neutrons because they're different isotopes of the same element. So if I were to grab a handful of carbon atoms, maybe in the form of, let's say, a diamond, all of the carbon atoms in there would not have the same number of neutrons. There would be different isotopes of carbon in there. And so really to be useful, we talk about average atomic mass. Average atomic mass. Sometimes people just call this the atomic mass, which is just the atomic mass of all of the atoms as they occur in their natural abundance. So it would be the average mass of all of the carbon atoms that I'm holding at any given time. And so we think of it's the mass of of all carbon atoms. There we go, or all atoms, considering their abundance. It's average. So if we have some carbons that have an atomic mass of around 12, some of atomic mass of around 11 or 13, and we just consider what their abundances are, their natural abundance, and we average their mass that way. Let's look at an example about for how we can calculate this, and I'll make it clear. So let's look at copper. Copper has two isotopes, copper 63, and this is just, before I continue with the question, this is just copper 63 is just another way of writing copper 63, where the 63 here is just the mass number of protons plus number of neutrons. It's just easier to write in a sentence with the dash. So copper 63 has a mass of 62.9291. It's not quite 63, but very close to it. And it has an abundance of 69.71%, meaning 69.71% of all carbons that we could find naturally are going to be copper 63. And then copper 65, which has an atomic mass of close to 65, has an abundance of the remaining 30.83%. So what's the atomic mass of copper considering these two different isotopes? Well, let's do that. All we got to do is add them up, take into consideration their abundances. So the atomic mass should just be the mass of copper 63, which is 62.9291 atomic mass units, times the abundance of 69.71%. And remember, percent just means divided by 100. And the second one, let's use a different color for that one. It's copper 65 with that abundance. So copper 65 has a mass of 64.9278 atomic mass units, and its abundance is 30.83%. So if we add this all up, let's just do this one at a time. The first bit here comes out to be 43.87 atomic mass units, right? Remember the units there. 4 significant figures here, more than 4 here, so our answer should only have 4 significant figures. And then this part comes out to be 20.02 atomic mass units. Again, 4 sig figs here, more than 4 here, so our answer should have 4 sig figs. So if we add these two up, the atomic mass of copper is 63.89 atomic mass units. Now we're adding up, so we just look at the number of decimal places. 2 decimal places, 2 decimal places, 2 decimal places. And that's our answer for number 6. The atomic mass of copper, take into consideration both of these different isotopes and their abundances, is about 63.89 atomic mass units. So if you were to grab a piece of copper, the average mass of the atoms would be about 63.89 atomic mass units. Try calculating the atomic mass of magnesium. Note that there are 3 in this problem. There are 3 isotopes we need to consider. Magnesium 24, magnesium 25, and magnesium 26, and these are their abundances. Try that for yourself, and when you come back, I'll just give you the answer to see where you land. Okay, so if you did this, and I'm not going to do the math, it's just multiplying these numbers by their abundances and adding them up, you should get an atomic mass of 24.31 atomic mass units. Whenever you write your answers, make sure you include the units, that's important, and the correct number of significant figures. In this case, it turns out to be 4. If you didn't get that correct, let me know and we can go over it together. But let's try number 8, because number 8 does it a little bit backwards. It gives you, for gallium-69, it gives you the mass and the abundance. But for the other isotope, gallium-71, it doesn't give you either the mass or the abundance. All it gives you is the average atomic mass of gallium as a whole. So here it's asking what's the mass of gallium-71. Try to see if you can work this one out by yourself, and then pause the video, try to work it out for yourself, and then unpause and we'll go over it together. Okay, so we can set this problem up the same way we set up the calculating the atomic mass. We know that gallium-69 has an abundance of 60.11% with a mass of 68.9256. And gallium-71, which we don't know the abundance and we don't know the mass, is what we're trying to find. So let's call the mass X, atomic mass units. So X atomic mass units times the abundance should give us the total or the average atomic mass, which is 69.72 atomic mass units. So what percentage should we use? Well, in most calculations, the total percent is going to be 100. And since there's only 2 here, 2 isotopes, and one of them have an abundance of 60.11%, the other gallium-71 should have 100 minus 60.11%, which comes out to be 39.89%. So that's what we're going to use, 39.89 over 100 as the abundance for gallium-71. So now that we have our problem set up, the only unknown that remains is what we need to find, the mass of gallium-71, which we stated is just going to be X atomic mass units. So this becomes an algebra problem, right? We do the math over here, and this comes out to be 41.43 atomic mass units, right? Because this is atomic mass units. Here, this just becomes 0.3989x. And over here, we have 69.72 atomic mass units. More algebra, we subtract 41.43 on both sides, 40 minus 41.43 AMU. And so this gives us 28.29 atomic mass units. We solve for x by dividing by 0.3989 on both sides. So divide by 0.3989, and that comes out to be 70.92 atomic mass units as a value for x. 4 sig figs, 4 sig figs, 4 sig figs, we're dividing. So that's our answer. The mass of gallium-71 is 70.92 atomic mass units. Now, just to verify that our answer makes some sort of sense, we know that it's gallium-71, so the atomic mass should be close to 71, and I would say 70.92 atomic mass units is very close to 71, so that makes sense. All right, let's think about how abundances work with the atomic mass of an element. So pause and see if you can figure out question 9 on your own. Carbon has two naturally occurring isotopes, carbon-12 with a mass of exactly 12.00 atomic mass units, has an abundance of about 98.93%, and carbon-13 with a mass close to 13 atomic mass units, an abundance of only 1%. Which of these is the closest, do you think, to the atomic mass of carbon without doing any calculations? Well, carbon-12 is almost 99% of all carbons that you're going to find naturally. So if most of the carbon you're going to find naturally is close to 12 atomic mass units, then the average atomic mass is also going to be close to 12 atomic mass units. I hope that makes sense, but to summarize, we looked at atomic mass, where the mass of a proton and a neutron in atomic mass units are about equal to 1. And the average atomic mass is going to be the average mass of all atoms considering their natural abundances, usually given as a percent. So if you just multiply their mass by the percent that they occur in, you can get the average atomic mass. In the next video, we're going to look at chemical formulas. I'll see you in the next video.